Hi everyone, my name is Brian Bednarski. I'm a master's candidate with UCLA Electrical and Computer Engineering, and today I'll be discussing my recent work titled On Collaborative Reinforcement Learning to Optimize the Redistribution of Critical Medical Supplies Throughout the COVID-19 Pandemic. I want to note that this work was done in collaboration with my two co-authors, Akashdeep Singh at UCLA and William Jones at UC Irvine. We completed this study in the fall and currently have plans to continue developing some extensions in future work. So if any feedback or suggestions come to mind as I'm presenting, please feel free to email me after this to discuss further. My goal for this discussion is to help those here develop improved intuition for prototyping population health management tools using a combination of AI and data outside of the traditional EHR. My hope is that by walking you through some of the motivations and design choices behind this study, you'll be able to reduce bias in predictive analytics models and develop computationally tractable reinforcement learning, or RL, algorithms for online applications. The COVID-19 pandemic continues to challenge nations with shortages of medical supplies to combat the disease. When faced with these circumstances in the United States, some public health officials work together to share their resources. However, as U.S. entities lack a unified system for equipment management redistribution, they resorted to rudimentary techniques such as phone calls and press releases to request help. This reactionary response strongly indicates a non-optimal redistribution of critical medical equipment. This problem setting seems well suited for deep learning solutions that can ingest massive amounts of data in real time and optimize outcomes for objectives that health officials can agree on in advance. However, naively approaching this problem with deep learning leads to two immediate issues. First, if we hope to deploy these models in the early stages of crisis, they must be able to learn quickly and make accurate inferences without much training data. Second, if system architects don't consider inherent biases in data during model training and validation, the same issues that drive inequitable care provision across regions and demographics in our country will be ingrained in the resultant models. I'm excited to share with you today how we work to mitigate the effects of reporting bias in COVID statistics and regional health inequities to train a series of models that accurately predict demand and simulate the redistribution of ventilators to states experiencing COVID case surges. When we began this project last spring, it was motivated by the severe global ventilator shortage that we were facing at the time. Thankfully, demand for ventilators shifted as clinicians identified the benefits of pronation for severe cases, but supply shortages during the pandemic were not limited to just ventilators. As a result, we'll be presenting these models in the context of ventilators, but the same solution could be applied to PPE, vaccine distribution, or surge predictions with minimal changes. With this context, we define three primary objectives for our model. The first is effective bias mitigation through the integration of comorbidity rates and other state-level population health statistics. The idea here is that if increased rates of comorbidities in a state lead to increased severe COVID cases, we want our model to represent and generalize that knowledge when making predictions for any state. Our second objective is to investigate the effectiveness of deep learning models in this real-time, complex multivariate setting. Third, we aim to build an RL algorithm to optimally distribute supplies from states with a surplus to those experiencing shortages. And finally, we also require that these models are capable of learning online using only the first 2 weeks of training data for pre-training before the initial inferences and decisions are made. These three outcomes translate directly to the three stages that make up our system pipeline for ventilator redistribution: data pre-processing and imputation, demand inference, and collaborative resource exchange. We make two statistical assumptions for a robust simulation environment. First, we use the number of COVID ICU beds reported on the first day of simulation as a proxy variable for the number of ventilators in a state, which is not a consistently reported metric. Previous studies showed that approximately half of COVID ICU patients required mechanical ventilation in the early stages of the pandemic. The low scale of this ratio allows us to assume ICU bed data as a proxy without dramatically changing the scale of our simulation. Our primary input to the data pre-processing stage are the daily reported statewide COVID statistics from the University of Washington's Institute for Health Metrics and Evaluation. This data also provides IHME's own projections for these statistics, but those were not used here. We include biweekly CDC metrics for statewide deaths above average to assist our inference model in overcoming statistical biases that result from regional differences in the number of COVID tests performed and cases reported. Furthermore, we include fixed values for statewide rates of heart disease, asthma, COPD, and diabetes from the 2017 census to account for varying rates of comorbidities regionally. We pre-processed data between February 4th and August 4th, 2020 for this study, using simple linear interpolation to guarantee continuity. We compare 3 different models in stage 2 to predict the ventilator demand in 3 days, the mean shipping delay. First, the naive approach assumes current demand to be the future demand. Second, we train a univariate Holt-Winters model to make the prediction, which considers only previously observed ventilator demands in a state for the respective inference. Finally, we designed a custom multivariate LSTM deep learning model for this regression problem. The LSTM takes 14-day sequences of observations for a state, which totals 105 fields for each day after pre-processing. Importantly, we train a single model generalized to all states. This 14-day input size represents the minimum amount of data necessary to deploy our system. In operation, we see that the LSTM performs exceedingly well compared to the naive and univariate methods. From this plot of daily predictive error from each method, we see that both rudimentary methods accumulate large daily errors corresponding to case surges in the early stages of the pandemic. The initial dip in the blue curve results from the rapid rise of cases in New York and New Jersey last March. Using a 3-day-old observation, the naive method underpredicts on a rising demand curve and overpredicts on a falling curve. The univariate method performs a little bit better, but still demonstrates underfitting and similar inflection points to the naive method. Finally, we see that the multivariate LSTM's errors are independent of this pattern, demonstrating that the model is generalizing input data well and making accurate predictions. Over the entire simulation period, the LSTM demonstrated nearly 12x and 5x RMSE improvements over the naive and Holt models, respectively. Next, we compared the predictive accuracy of the LSTM across every state and found that New York and New Jersey were outliers in an otherwise relatively well-grouped distribution. It's not surprising that the LSTM behaved this way, because New York and New Jersey's spring surges occurred simultaneously, and the model had no comparable training data at this point. However, from the plots on the previous slide, we still observe that the LSTM learns relatively quickly for these states and avoids any consistent long-term error accumulation. Here's a scatter plot with the same RMSE for each state versus the cumulative 2017 census rates of the comorbidities mentioned earlier. The fact that there's no obvious trend between the cumulative comorbidity and predictive error of our LSTM shows that our model is at least not biased with respect to the comorbidities that we allowed the model. We performed the same analysis for each individual comorbidity to similar conclusion. We first designed and evaluated 3 intuition-based algorithms to serve as baselines to compare our RL approaches. These 3 algorithms redistribute supplies by only sending ventilators from states with a surplus to those with a shortage in order specified by the predicted future demand in each state, maximum need first, minimum need first, or in random order. We next designed 2 decision policies based on traditional RL algorithms, value iteration and Q-learning. The primary difference between these 2 approaches is that the Q-learning algorithm follows a lookup table to compare actions, while value iteration recursively explores all possible actions until convergence to provide a map for the most valuable action in every scenario. Q-learning outperforms value iteration in this application and is more computationally tractable, so we'll focus on that algorithm in the following slides. The Q-learning algorithm uses state action pairs from a traditional Markovian RL problem formulation to approximate the relative value of all possible actions. For the purpose of this presentation, I just want to present this Q table as it upper bounds the complexity of evaluating our Q-learning algorithm. We define the status of a state to be the ratio of ventilator supply to demand in that state on a given day, and quantize that ratio to one of 20 finite states between the integers 0 and 2, resulting in the daily status having a dimension of 20 times the number of participating states. With an action being defined as a binary state-by-state transfer matrix, we ultimately are left with a Q table of dimension 20 n states cubed, which was tractable for up to 50 states and performed well. Rewards observed by the agent are determined by the change in total quantized state status ratios following a mapped function of the quantized state to the inverted exponential decay curve shown here. This mapping allows us to incur exponentially lower cumulative rewards on each day. This scheme for rewards discourages shortages exponentially while encouraging the algorithm to buffer ventilators even when they may not be experiencing immediate shortages. The following supply-demand curves show the Q-learning algorithm distributing supplies in a single 4-state simulation. As you can see, this simple implementation tracks demand across the states remarkably well. Early in the simulation, California, Texas, and Florida rushed to share supplies with New York, which was experiencing a demand uptick that the total supply across all 4 participating states could not satisfy. However, after this demand surge, ventilators are redistributed back across participants, and no additional shortages are observed. While there are still some examples of unnecessary exchanges towards the end of the simulation, we might expect this considering that there's nothing in the algorithm reward function penalizing unnecessary exchanges. We compare the performance of each redistribution algorithm in a series of simulations selecting 5, 20, 35, and 50 states in random order. 1,000 simulations for each. Using our best case demand predictions from the LSTM inference model, the same series of simulations is run for each redistribution algorithm. Shortage reduction compares the observed shortage with the algorithm applied to the shortage that would have been observed with no actions taken. Optimality compares the observed shortage with the algorithm applied to the shortage that would have been observed with a theoretically ideal use of ventilators and no shipping delays. We see that the Q-learning algorithm improves consistently in both average performance and standard deviation as the number of random states participating increases. Throughout these simulations, Q-learning consistently demonstrates an average optimality ranging 93 to 95%. This plot compares the shortage reduction of Q-learning versus the intuition-based policies. With 5 states participating, allocating the maximum need first tended to perform slightly better than the Q-learning algorithm. We believe that these intuition-based approaches are well suited for the logical simplicity of smaller simulations, but as the number of states increases, their performance degrades with respect to Q-learning, which is ultimately our best model in simulations with 20, 35, and 50 states. In summary, I want to revisit a few assumptions, limitations, and directions for future work. As stated earlier, we make 2 significant assumptions for our simulation environment in order to present an analysis with real data, using scaled ICU data as a proxy for ventilator supplies, and using a consistent Gaussian shipping delay model. We did discover some limitations of our models along the way. First was a value iteration convergence issue, in which we sacrificed the accuracy for realistic convergence times and found the algorithm to be unpractical. Second, we find that the lack of a centralized system for reporting supplies across state-level entities required us to use the proxy variables I explained earlier. Third, training time for the LSTM is also a limiting factor under our current implementation as the number of training samples grows with time, and a new batch training algorithm would be necessary for longer simulations. So we're left with a few clear extensions. First, we'd like to investigate the outcome of some nonlinear imputation methods and analyze performance with respect to data sparsity. Second, as mentioned before, extending our Q-learning algorithm to a deep Q implementation could help improve performance when faced with more complex dynamics. Finally, there's obviously a lot more work to be done with regards to analyzing comorbidities and the equitability of healthcare throughout the pandemic, and we are definitely looking into furthering that investigation and open to suggestions for future work. So with that, I'd like to thank you for your time, and please email me with any questions or comments. Thank you.